before we end the last talk. We're going to do last call for all the merchandise and hardware hacking and for shirts at registration. Last time to buy those is about 4:30, so make sure you get over there before then if you want one of those. And now let's give a warm welcome to Machinist, talking on Swords to Plowshares, Repurposing the Ghost Gunner.
Hello, friendos. Good to see y'all. Hope you're having an enjoyable LayerOne thus far. Like, we're all still here and alive, so I guess at least us in this room are doing good. So, welcome. This is Swords to Plowshares. So Ravine unfortunately couldn't be here with us today. He had to go off to Canada, go do some floppy head BDI thing. So it's just going to be me, but that's okay. This is Ravine's machine, and he's the one who knew a whole ton about it, so that's why I tried to include him here. Me, myself, my background, as you can guess, I do machining type things, and this is actually a little benchtop CNC machine when you look at it under the hood. So any like Second Amendment friends out there in the crowd? Yay, a couple of you. Happy Memorial Day if any of y'all served. So let's see. If you're familiar with a ghost gunner, it's a CNC mill, but it's very purpose-built. It only does one thing. It only is supposed to make an AR-15 lower receiver. Specifically, it converts one that is starting at an 80% finished complete state that the ATF doesn't care about, you don't need to have a serial number on it, to plop it in this machine, execute some code, and bam, now you have a piece of metal that goes bang and has no serial number on it. So the purpose of my talk, however, total disclaimer, I'm not a gun owner, I'm not really that much of a gun guy, I think mechanical things are kind of cool. So what I did here is I RTFM for you. Looked underneath the operating system here. It runs Gerbil, and through this talk I'll show you guys how to operate this machine like a generic CNC machine. So random inspirational quote, great. Already babbled this about you guys, definitely a gray area of the law. Especially in California nowadays, I think the whole law's changed where everything has to have a declared serial number, and you know, it's bad news if Johnny Law finds you with a piece of metal that goes bang and it tends to be undocumented, but you know, the dang libs, right? So we've all heard of the AR-15. Some of us probably have them or seen them. Usually it's in the context of this being like an assault weapon, right? Like the AR-15 model was specifically designed as a military weapon, I believe, or the M16 format, and the AR-15 is derived from that. Anyway, it's a popular format out there, but you know, just like assault weapon is, hacker is kind of a scary term for those of us not in the know, so who cares? So just a couple examples. AR-15 comes in either rifle or pistol format in various shapes or sizes. These are just a couple of the, you know, the Fortnite add-ons you can get for these things, Fortnite skins. And this is the 80%. This is the block of metal that nobody really cares about. It's missing a couple of crucial features that allow it to be a firearm. Particularly, there's a couple of holes on the side here, and from the top side that you can't see, there needs to be a big piece cut out for the mag well, so like the trigger operating mechanism can work. And that is why this machine here is in such a weird, funky format. It's brick shaped because that's exactly what it's meant to fit, nothing else. So we're talking about sketchy pieces of metal, right? Just like a lot of us are familiar with, you know, our random, you know, Kazaa BitTorrent downloads we've done over the years. You know, there's also such things as like sketchy numbers, sketchy ones and zeros, and in this case, sketchy pieces of sheet metal. So this is just one example of sketchy pieces of sheet metal that go along with the AR-15 group. Do not put this thing in your gun. Do not have this thing at all without a tax stamp on it, just warning you. Same thing with this little sketchy piece of metal. I don't know where we could ever find a sketchy piece of metal to drop in another sketchy piece of metal, but yeah, don't make these things at home either. This is a sketchy piece of string. As you can see, it has an ATF tax stamp on it, so like, don't attach these things to your guns either. So when we're talking about the AR-15, like, sure, all the blueprints and 3D models are freely available online. You know, it's not like a mystery how these things are constructed. But eventually you get confronted with a blueprint like this. And for us non-engineering types, it's a little messy. It's like, well, you know, there's a lot of details here, but what's the most important detail? That one. So a little bit about the Ghost Gunner's history. Have you guys ever heard about a 3D printed gun, Liberator? You guys remember that from the news a couple years ago? This is the same group. So those guys that created the 3D printed gun, they're like, haha, we're gonna like give this file out to the masses and the government can't, you know, stop us. So great, that's wonderful, but I can't think of a single time where a 3D printed gun actually did anything useful out in the wild. Like we saw a couple of demonstrations where it was like Looney Tunes style where the barrel, you know, flowers backwards and explodes all over the place. I mean, it's plastic versus gunpowder, right? Like, use your common sense. So the Ghost Gunner was kind of the next step of evolution of the process. Well before the Ghost Gunner, people have been finishing 80% AR-15s, you know, on their drill presses or their Bridgeport milling machines. So it's nothing new, right? You can do this by hand if you are patient enough and skilled enough. What the Ghost Gunner actually does is sort of packages everything up into a tidy little thing that you can send in UPS. Or actually, I'm not sure if UPS sends these things anymore. That used to be a point of contention. So, like, if you have a Bridgeport mill, you can pretty much make anything in the universe if you have, you know, the old-timer knowledge of how to use the darn thing. So that's what pretty much kept the ghost guns out of the hands of a lot of people, because, you know, most people don't have, you know, the time or the skill set or, you know, a garage floor with, you know, concrete and three-phase power they can hook up their Bridgeport milling machine to. So it's usually been relegated to, you know, hobby machinists or, you know, people with access to a small factory. And technology is at a point where, you know, all of this is shrunk down and economized enough where, hey, we got a benchtop CNC machine here for, you know, less than $2,000 that, you know, makes things that go boom. One of the challenges with building one of these machines yourself, an AR-15, is if you don't do some of those holes just right, you get a particular method of error called hammer follow. And there's a California state precedent about that. If the trigger isn't assembled just correctly, or if something's a little worn out, when you pull the trigger, it doesn't just go bang, it goes bang, bang, bang. And that's a bad thing, especially when you're at a range and there's people around you who are listening for that kind of thing. So a U.S. Marine actually did time for something like that. He loaned a gun out to his buddy. His buddy wanted to buy it. He's like, yeah, take it out to the range. Go, you know, shoot a couple rounds through it, see how it goes. And it was old and worn out. Buddy takes it to the range and bang, bang, bang. And the cops say, oh, you know, do not pass go. You go directly to jail for an unlawful transfer of an unlicensed automatic. That's what that guy ended up getting hit for. So just be careful with this kind of stuff, right? It's pretty heavy. So like I was saying, the Ghost Gunner here sort of packages up that skill set. Like, not only is a manual milling machine hard enough to use, but running a CNC milling machine in a meaningful manner is, you know, another level of difficulty beyond that. So the Ghost Gunner intends to take sort of the finesse, sort of the artwork out of that process and programs it into a bunch of code. Inevitably, it all boils down to like a bunch of three-dimensional connect the dot, you know, motions just guiding a cutter through a piece of metal. So as long as you're following a couple of conditions, you can do it, you know, countably infinite ways, but there are uncountably infinite ways to do this wrong. So I'm not going to show you the entire art of CNC machining, but I want to show you a couple of the steps, especially with a machine like this, which is an impressive piece of hardware, to use it for more than just something that makes firearms, that makes weapons. I want to show you how to use this as like a general purpose milling machine. So why this thing, right? Like there's all sorts of milling machines you can get off of like eBay or Alibaba or whatever. Like, what's so special about this thing? Well, first of all, I'm not sure if you guys saw me lugging this thing in here. It's massive, and with the milling machine in particular, you want the units to have some lead in their butt, right? Like, that's what makes the difference between like, a Harbor Freight lathe versus, something that was made in America in like 1930 that's like 10 times the size. Even though it's about the same work volume, you need that kind of a weight behind a machine to counteract the cutting forces, right? Like there's minimal but significant cutting forces at the cutting edge of the spindle on this machine, and the mass of the rest of the machine behind it is doing all the resistance against that, not only the motors but the screws and the actual frame itself. So it really needs a big, thick, beefy frame with nice thick linear rails to resist all that, to keep from flexing once it's engaging in the cut. So I mentioned ball screws, so that's something kind of unusual in a machine this size. Usually what you find in a machine this size are Acme rods. They're like 29-degree linear transfer. It's a very special shape. I'm sure you've seen them on screw threads on old machines, but the difference between ball screws and Acme screws is ball screws are a higher level of manufacture. They're more precise, and specifically there's no slop in any ball screw. With an Acme screw, if you reverse motion, there's a little bit of slop in between the male and the female parts. So a little, when you reverse motion, nothing happens until like the slop in the mechanism gets taken up. And with a ball screw, you don't have that problem. There's precision moving parts, and the screw itself is precision ground or precision rolled, probably in this case. And it just allows for a higher degree of control of the motion. And with the one key difference with a CNC machine having ball screws is that allows you to do climb cutting. So typically on like a Bridgeport machine, you need to have the cutter loaded up in a specific way, so all of the slop is always up against one side of the screw, and you can only take gentle, moderate depth cuts using that technique. But things like CNC machines, they can go the other direction. They can climb cut with carbide tools and make use of the inherent rigidity of the machine. So that's kind of a neat departure on the manufacture of this machine. The one thing that doesn't really make a whole lot of sense is ball screws using stepper motors. Now, if you're using ball screws, you would typically want to have servo motors guiding them behind them, because servo motors are continuous and they hold firm in all positions, where a stepper motor holds firmest at its discrete rotation location, right? It doesn't have, it has any one of like 200 possible locations it can go through its entire range of rotation, any one of those discrete locations. But while it's moving, it doesn't have nearly as much holding torque as when it's holding still. So just one of the little departures of the two motor types. And you would expect to see something like this on a lower grade piece of hardware, because stepper motors do not need any kind of feedback. They don't need a closed loop system with encoders talking on the shafts that make the machine know that it's in the exact position that it's commanded to be in. That's something you would find on a much higher end piece of equipment. Definitely something that's not running on Arduino hardware. So another nice thing about this is that it has a nice fat cartridge bearing. Usually on those Chinese milling machines, you don't really find nice spindle equipment. I had a Max NC. Actually, I think it's still a 23B, and it had like a Singer motor, like a sewing machine motor stacked on top of it. So the spindle wasn't anything to write home about, and the motor on top of it was just kind of like falling over sideways. So this has a nice brushless DC motor and a cartridge bearing, something that would be indicative of the rest of the inherent stoutness of this machine. So the G-code interpreter is kind of the thing I'm going to focus on a little bit more. Gerbil, it's a very lightweight, fits on an Arduino Uno, but it's optimized to be able to do all the CNC processing locally. The problem with running a CNC machine is you need to have low latency hardware to keep up with the stepper timing and making sure that you're not missing any steps. So people have spent quite a bit of time developing the Gerbil environment just to be like a lightweight CNC controller. Mentioned a couple of these things already. G-code is essentially three-dimensional connect the dots, whether you're running a mill or a lathe. Mill code is a little bit more obtuse. You're generally looking down the spindle. X and Y is how things are moving around, and the Z-axis is perpendicular with the spindle. Typical G-code has a couple of interesting behaviors not typically seen in programming languages. So there's groups of code that exhibit modalities. So G0, G1, G2, G3. I'll get into these later. They're all within the same group. If you call G0, which is a rapid move, make the machine move as fast as you can, that overrides any of the subsequent commands, G1 or G2 or G3. And conversely, if you're in G1 mode, which is a linear feed mode, it overrides G0, G2, and G3. So that's just one of the strange behaviors about G-code. I'm not going to go too much in depth, but it's just something to pay attention to, is the different groups and like which codes are sticky, which ones are active by default in the background. Another thing to consider is whether it's this Ghost Gunner or any machine out there, you sort of have to use it within its work envelope. This machine is not all capable, right? It's specifically a purpose-built machine to do, one very specific thing. And because of some of the limitations of mostly the processing power, you can't really, drive it around the track full throttle. You have to give it, some gentle, dumbed-down commands just so it does what you tell it to. And one of the hard parts about working with these machines is like the inherent troubleshooting process, right? Like whenever you're on a new control and you're feeding it some code and it doesn't really give you a discrete output, you're like, oh, what the hell is going on? That's the part that really sucks down all your time. So just knowing how the machine works within its limits will save you a lot of time, whether it's the Ghost Gunner or anything. So I mentioned the spindle. So being a machine of limited capability, if we were just executing some manual commands to turn on the spindle, I say S1000M3 if I want to turn on the spindle at 100 RPM, nothing would happen. You RTFM and you can see that, oh, the spindle only has an operating range of 3 to 10,000 RPM. The spindle is also kind of low powered too, right? Like 125 watts max, and you generally don't want to run these things more than 50% continuously. So we're talking, 60 watts of total cutting power. It'll get a little bit of work done, but you can't ask a whole lot of it. That's what I'm saying. Oh, and the other thing I noticed while troubleshooting this talk of the last couple of days is there's no soft limits on this thing. Like there's limit switches as it goes and finds home, but you give this some bad code, it will happily try and like run off the ball screws the other direction. It was a little troublesome trying to fix it. I think you guys saw me fussing with this when I got started. So G-code can be quite diverse. Every letter in the alphabet appears in the G-code as a word in one form or another, but anything preceded by G is sort of the most important going on. The most important details going on. And right here I've summarized the eight most common G-codes you would use in this case. So the motion commands right up top, G0, G1, G2, G3. G90, G91, those are also important when you're doing some diagnostic moves. So the difference between absolute and incremental positioning, right? Like if I'm home and I say move 1 inch, okay, it'll move 1 inch right there. Say move 1 inch again and it doesn't move any at all. That's because I would be using absolute programming, right? It's 1 inch in machine coordinates. But if I say G91, move 1 inch, okay, move 1 inch again, oh, it moves an inch again, so on and so forth. A couple of larger commands that are important to know. So G90, G53, X0, Y0, Z0. So that's send the machine to its home coordinates, just an important diagnostic. G20 or G21, I'm not sure if this machine even reads in inch mode, but I wasn't even going to try, just fed everything in millimeters and everything's happy. Couple important conversions to know. For converting one way, you multiply by 25.4. Converting the other way by 0.03937, you're fine. You don't need a calculator beyond that. G54 that calls up the work coordinates. So not only does the machine have its own work coordinates all starting at 0, but you can also set your work coordinate, like if I had a part in here or a little thing I wanted to draw, and instead of 0 being all the way at the ends of the travel of the machine, I wanted the 0 to be some arbitrary spot. That's what you would use. You have to set G54 with a command found at the bottom of the screen here. That's the one peculiarity about running Gerbil that you generally don't have to deal with on a typical CNC machine, is having to set the coordinates inside of code. It's possible, just kind of one of those weird reach around things you have to do with this machine. Just above that, S5000M3, just a typical spindle command. 3 to 10,000 RPM is fine. It even does a reverse, which is kind of neat. All this stuff is listed in the Gerbil help manual. I think this is running Gerbil 0.9. The most recent Gerbil version is 1.1. I don't know if there's a distinct difference. This is also the Ghost Gunner version 1. They're on now version 2, which not only makes the AR-15, but the AR-10 platform lower. So kind of an interesting thing. So just doing some diagnostics, the homing sequence is the very first thing you need to do, right? You try and, you get everything connected, you get it all powered up, and it doesn't talk to you until you do the homing sequence. It just has to check where it is in space before it starts doing any counting or any motion. You might have saw me fussing around with this earlier. I actually gave it a bad command and it hit the limit switch, and when the machine hits its limit switch, it won't respond to anything else except the $X command. You have to like override the limit switch and give it a move so it can move off the limit switch. It's easy at that point to give this thing a move in the wrong direction if you don't know your coordinate space on this machine. I'll get into that in just a minute because this thing's kind of wonky. A couple other things about checking the modes and the settings here. Also, the cycle start and the feed hold command is important. You can feed hold in the middle of a program and it doesn't like reset everything. It just kind of like pauses there for a second. So feed hold, cycle start, you know, they're sort of latching back and forth. So what is this coordinate space on this machine? Typically, when you look at like a 3D printer or a vertical CNC mill, your coordinate space follows the right-hand rule. If you stick your right hand out like this, your thumb points in X, your index finger points in Y, and your middle finger points in Z. And your fingers are pointing in the positive direction. So Z plus, X plus, Y plus. Now, the right-hand rule is pretty typical on most machines, and the Z-axis is perpendicular with the spindle, right? It's along the spindle. With this machine, well, the spindle isn't vertical anymore, it's a horizontal spindle. So the coordinate system gets rotated in some really weird way like that. And that's the one wonky thing about this machine. It's possible to get the axis masks swapped. So the long axis would typically be X and the short axis would be typically Y, but in this machine, the short axis is X and this distance is Y. Not that big of a deal. You just kind of do the rotation either in your head or inside a cam or whatever. It's not a big deal. Either way, X and Y. So one of the other peculiarities of this machine is the orientation of the table. So not only does it have the strange vertical orientation, but the table isn't parallel or isn't perpendicular. It's parallel with the spindle, so it actually needs a secondary fixture so we have access to the typical X and Y axis. And just before I got on this talk here, I finished up a 90-degree angle plate for this machine. It was 3D printing in the other room, so literally finished like 20 minutes before the talk's done. There's also another feature on this machine where it does probing. That's one of the neat tricks it does when it's running through the DD program to actually create the AR lower. Is it takes the tool and connects it electrically through the system, and when the electrical circuit is completed, it knows, oh, okay, the tool is touching metal, and that is a specific location, right? That's like the top of the part. or what you would typically call Z0. And it can even do the same thing, finding the edges of pockets. It would have to do a little bit of math using some of these macro codes we were looking at, but you can also like find the center and webs of a pocket that way. And I actually don't really have a use for probing, but it is a neat function that this machine has that most machines this size don't even bother with. Like I said, beefy as heck, double X motors on the X-axis. So there's 2 ball screws and 2 motors here. They could do a lot more work than you'll ever theoretically put in this thing, but just one of those nice big beefy pieces of equipment when you look under that hood. Covered all these points already. Do want to touch on this machine being open loop. So what do I mean open loop versus closed loop? So closed loop machine would be servo driven with encoders, a lot more electronics going on. But why are we even talking about that? With steppers, if you ask too much of them, like if you tell them to make too heavy of a cut and the motor can't keep up, the stepper loses its position. So over time, everything starts like shifting through your work, right? Everything is going to be offset and incorrect from that point on, where a servo is like keeping track and compensating for that. So again, one of those reasons why you need to work within the envelope of the machine's performance is you try and make it do too heavy of a cut and you're going to be chasing your tail with stepper position loss. Nothing you can really do about that other than just take light, gentle cuts. One of the strange things about dealing with Gerbil is having to jog the machine around. Like usually when you see a machine like this, there's either like some sort of jog console or some way to just like press a button and it moves across in one direction. And this machine doesn't really give you that option, or at least through the Gerbil sender I'm using. There's multiple different Gerbil senders that you can use. You can even talk this thing straight over a serial console and give it one command at a time, but I find that to be a tedious waste of time. Let's see, what else? Okay, so I'll shut up and move the machine around and we'll see what it does. Machine is now talking. Actually, let me start. Let me back up a second. Show you the hard way first. Okay, if you guys are more familiar with talking to Arduinos or Arduino IDE, Control-Shift-M. So this is our serial console. You could even do this over PuTTY if you like. So I sent it the $H for the home sequence. The machine does its little dance, finding the home switches and backing off and double checking its location. Okay, cool. Now, from its machine home position, the machine home position is different than the limit switch position. So being able to send this to machine home is G0 go fast, G90 go in absolute coordinates, G53 in machine coordinates, X0, X0, Y0, Z0. Okay, machine is now in its 0 position. Doesn't tell you a whole lot here. So that's why I like something a little more verbose than a serial console. Universal G-code sender is what I ended up using for this project, but there's dozens of different flavors of G-code senders or whatever that will talk to Gerbil. Anybody familiar with Linux CNC out there? So this is distinct from Linux CNC. It doesn't, you can't really talk to this with Linux CNC because Linux CNC is doing all the motion processing on the computer and just sending all of the stepper commands directly over the serial, where I'm just sending lines of code and the machine here on the Arduino board is processing all the motion control. So just something to pay attention to if you have any intent on integration later on down the line. So same kind of deal here. Oh. Come on. Okay. Okay, we're connected. We got an alarm because we haven't gone through the home sequence yet. And here's where it gives us our jog console. So this is the point to remember. It's like, okay, it's at Z home. What are the machine coordinates from Z machine home? Most machines out there in the world will have all of their coordinates in negative space. This is one of the most important details I have to share for you. Because if you move in positive directions from its home position, you're going to start hurting the machine or losing steps. And it's just one of those peculiarities, right? The machine will happily move in X minus and Z minus and Y minus. Now, what happens when I make some noise? All right, we're going to tempt the demo gods here a little bit. We're going to see if we can hit a limit switch and get the machine fixed. I think we have to command it line by line. Right? No limit switch on Z. Oh, this doesn't even care about the limit switches. Okay, well, cool. We tempt the demo gods, and I'm not going to tempt them any more than that. So the terrible clicking noise you heard was stepper loss, right? Like the machine was trying to move, but the actual mechanism of the sliding parts were blocking. They were getting in the way. There was no more physical room. So the clicking was the actual motors just sort of vibrating in an uncomfortable way. A rule of thumb with these machines is when they're operating correctly, they should sound like white noise, right? Like shh or where, like when they're complaining, when something's wrong, they start screaming for help, or it sounds like drums in the background, like Jane, stop this crazy thing. So just keep that in mind. Even like a 3D printer, when they're not operating correctly, like when you get like a filament jam, they start like clicking and clacking instead of like making happy little sing-song noises in the background. So just one easy way for the inexperienced mind to know when something's going wrong with a complex system, right? Okay, so we can move this machine around, great. Like I just screwed it up because we lost some steps, so it's sort of like lost where it is in space. You just run the homing sequence one more time, and hopefully it doesn't make those terrible noises, and oh, okay, it found its home, good. So once you know the orientation of this machine, once you know its limitations, you can just program it in a typical CAM system. You can program it by hand if you want to do the G-code line by line and connect the dots. That's totally possible. While my fixture was finishing, like half an hour before my talk, I got some Hello World program here lined up, just treating it like an engraving. So I just took an arbitrary tool that was already in the programming toolbox. This is a Fusion 360, by the way. It's what I like and what I use. Basically, any program that outputs G-code will eventually cut your part. It's just, how much do you want to bash your head up against the keyboard to get to that point? So I'm just having it follow the diagram of Hello World. Nothing too special about it. And most competent CAM systems will also output G-code meant specifically for the Gerbil processor. Lots of fun, robot talk, right? And that's just connect the dot code describing, where this thing's moving around in space. I did mention earlier about the one trick needing to set work coordinates. So assuming I had a fixture like this, and I wanted to place it somewhere here on the part, I need to call a specific work coordinate at whatever location my part starts, right? Like I'll do this here in a minute after the Q&A just to sort of complete the cycle, but I got some blank playing cards here from Mr. Bot, and we'll do some Sharpie engraving on this machine. So being able to call up a specific work coordinate, I'll just show you that brief process real quick. So, oh, don't go that way. Third time's a charm. I had a serendipitous moment with this machine earlier. Like, I was racking my brain, like, how the hell am I going to attach a Sharpie to this thing? The spindle's a little too big. I'm just going to have to duct tape some bullshit on the outside. Like, what the hell am I going to do? And as soon as I let the breath out of my body and sat down just right, like, my eye lined up with like one perfect line through the sheet metal here, and I could see like the most perfect Sharpie size hole. I put the Sharpie in there and tiniest little bit of wiggle room, right? Like right next to the spindle. Perfect. Like I'm not sure if you can even see it in there, but just right. I actually had to cover it with a little piece of tape just to take up that last little bit of slop, and it's even backed up on the backside. And that was the most beautiful thing that's happened to me all week. Just perfect fit, right? So the machine is home. We'll return to 0. And we'll just jog it around to some random location. I mentioned this code earlier. Right here, this is the magic code, G10, L20, P1, X0, Y0, Z0. So whatever coordinate the machine is at, you execute this code, and it overwrites that specific coordinate into the G54 work coordinate. G54 is the typical work coordinate that you would be using. It's just like number 1. So I would call that out right there, and the machine would begin that program from that point. Now that's what I didn't show you in CAM, is remember my right hand rule. I'm not sure if you can see this little triad over here. A little triad over here in the left-hand corner. That's showing my work coordinates, so X, Y, and Z, like that. So if we're looking in the same orientation that the machine's set up right now, this is how it would print, right? Or actually, that's how it would print, Z in line with the spindle. So I'll do the boring, slow printing later. That's fine. Now, have you guys been listening to this, right? I said that the machine operating correctly, it should sound like music. It should just sound like something intentional is going on. The stepper motor in particular is kind of interesting, right? Instead of being a discrete unit like a high-end servo motor would be, the stepper motor has like discrete little steps. Every time it's revolving, right, it hits every one of those steps along the way. And you go click, 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 click. You do that fast enough and you produce a tone, right? Now the interval between the clicks is no longer, click, silence, click, silence. It all just kind of blends together to being one tone. And if you program these machines at different rates, they'll generate different tones. The problem is, like, if you want to get really fancy with it, you can program 3 different motions, 3 different lengths of movement, so you get 3 different sets of clicks, but you can only program 1 feed rate per line. So if you want these things to be able to sing, there's a special little website, lemonparty.org. This guy right here, if you feed a MIDI file into this guy's conversion program, it outputs music for you. But the thing is, you have to be able to feed it the machine parameters, the steps per unit, and the maximum travel is the important part. So without knowing the parameters of the machine, without knowing the limits of the machine, you could potentially damage it. But I'm not sure if you noticed when I booted up my G-code sender here, this is kind of neat. So I connected to it, and it suddenly gives me all the parameters here, especially the important ones, 400 steps per millimeter and the XYZ travel limits. Okay. Actually, I'll go with my prepared stuff. I'm not going to attempt that demo guide just because of this troll right here. Now, first one to guess this song gets 4 internet points and wins for the day. And that's what the program looks like. That's the motion it's going to make. No. Even guess the author. Bingo, the troll up front wins a beer. Okay, so I think that's the end of my demo here real quick. I'll open this up for any Q&A if you guys have any specific questions or comments or anecdotes or possibly lewd jokes, I don't know. That's 1001, that's the violin solo. Using that home constructor website, knowing the parameters of the machine from either calling them up using the #S or just looking at the console log. And after you input a MIDI to this right here, what is it called? MIDI to G-code. You input a MIDI and the parameters of the machine. So I'll just plop in a MIDI here real quick. So right here we would say 400 steps per millimeter, and X is 0 to 60, so we'll say 0 to 50. Y is 140, we'll say 100. And the other one will say 50. Only looks like there's 2 channels on there. Give this thing a couple of clicks, and we'll generate some code. Now, this is another reason why it's important to know your machine, because, obviously you don't want to run any random G-code on your machine for, sake of damaging the thing. So I've been sitting here ranting and raving about the coordinate system and how to deal with all of that. This code is beautiful. It does wonderful things. I would never even imagine trying to do that by hand, but the problem is all the code is in the positive coordinate space. So you just do a quick like search and replace and flip every x to an x minus and you're good. Just make sure that the line right there that says x0, y0, z0 does not have -0. Computers don't like that. Okay, any other questions? What's a ball screw? So let's ask Google. So ball screw. So instead of just like an old school like transmission device, the ball screw it has like very nicely ground parts and like a recirculating ball mechanism, so there's no slop, right? There's zero backlash, but they're more expensive, they're harder to manufacture, they require a little more care, rather than the old school Acme rod, Acme thread. This is what a ball screw is used instead of, right? Not ground with a radius and the matching part looks just like the reverse, right? This is the old technology, or the low end stuff. Any other questions? Will do when I finish up. Mm-hmm. Why would I not want to run random G code, and what would malicious G code look like? Well, it turns out like G code by itself, it's kind of limited, right? It's a scripting language, but you can change settings, you can do other weird things. This machine doesn't speak it, but most G code also uses what's called macro programming, which is like assembly G code. And you can do logic and pass variables and like look at the insides of a machine using that kind of stuff. So you can do some nasty, nasty stuff with macro languages. That's for sure. Anything else? All right, y'all have been great. Thank you. Oh, encore for the machine if you want to stick around. That's tempting the demo gods. Okay, guys, that's what I got. Thank you.